Okay, gravitational fields. This is the first of 3 videos about what we need to know for gravitational fields. What is a gravitational field? It's a region of space where masses experience forces. There's a mass, there's a force, it's in a gravitational field. An electric field, charges experience force. In a magnetic field, there's a few things, currents and moving charges and other magnets. In a gravitational field, masses experience forces. And we define the strength of the field as the force per unit mass, and little g is the strength of a gravitational field strength measured in newtons per kilogram. So G equals F over M, or F equals mg, which you hopefully recognize. We can say a field is uniform or non-uniform. A uniform field, little g, is the same everywhere. The diagram on the left, the field strength is 9.8 newtons per kilogram everywhere. It's a uniform field. We see that the field lines are straight and parallel and evenly spaced. The second diagram, that is a non-uniform field. We see that the field lines are getting further apart. Bear in mind that, it's not a 3-dimensional diagram, it's a 2-dimensional representation of what's going on. But there's your gravitational field lines. As we move away from the Earth, the field follows what we call an inverse square law. Its field strength is proportional to 1 over r squared. If you double the distance, it's a quarter. If you treble the distance, it's a ninth. It's called an inverse square law. And we'll see later this equation, little g is gm over r squared. Big G is a very important constant. M is the mass of the Earth, and r is the distance from the center of the Earth for little g due to the Earth. Forces between masses. This is Newton's universal law of gravitation. All masses attract each other with a force which is proportional to the product of their masses and inversely proportional to the square of their separation. But easier to write it mathematically, F equals big G m1 m2 over r squared. R is from center to center. Worth pointing out that from Newton's third law, the two forces are equal and opposite. Newton figured out this relationship by looking at the orbit of the moon and the planets. Kepler's laws helped a lot, but he didn't have a value for the constant, big G, which is Newton's universal gravitational constant, and it took a very clever experiment by somebody called Cavendish to get a value for big G. And we have it now, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Now, looking at this equation, if we say one of the masses is a kilogram, then this will tell us the force per kilogram, and we will get the expression I mentioned before, little g is gm over r squared. Here's a question. So there's some data about the Earth, and basically calculate little g at the surface of the Earth. Calculate the mass of the Earth. And at what distance from the center of the Earth will the field strength be? A quarter of what it is at the surface. So have a go at them. And for the mass of the Earth, you should get about 6 times 10 to the 24 kilograms. Interesting, before Cavendish came up with a value for big G, we didn't really know what the mass of the Earth was. And when we found the mass of the Earth, it turned out to be nothing like we thought it was, because we didn't know that it had a metal core. And as little g follows an inverse square law, if you double the distance, then g will be a quarter.